Hi there. All right, so now what we're going to do is start chapter 2. And that rhymed. Okay? The first couple sections are actually kind of repetitive, but I want to take my time going through them. I claim that we've actually already discussed many of these ideas, but we're just going to formalize them. And then, as always, I'm going to go through a whole bunch of examples just to be sure that you're all clear. Okay? So, chapter 2 is all about functions. Remember that machine that I drew way back when in section 1.1? Okay? Where we had this machine that worked really hard and we had our inputs and we had our outputs. Well, section 2.1 is actually titled Input and Output. So let's pretend that we have this machine, and I'm already telling us the rule for the machine. Okay? In other words, if I put the number 1 in, and this machine works, well, I get 1 squared plus 1, or 2 that comes out. If I put in -3 into my machine, well, -3 squared is 9, plus 1 is 10. Okay? And we could keep going through and doing this. Now, as we've seen, there's better notation. The way we would want to write this formally is we would say f of x is x squared plus 1. Okay? Now, how would I write this input-output business? Okay, the thing to note is x is our input, and the entire function, f of x, in this case here, is my output. So, for example, if I wanted to compute, let's just take the -3, f of -3, well, as we've done before, I'm replacing x with -3, and if I do that on the left side, I need to do that on the right side. Well, -3 quantity squared is 9, plus 1 is 10. Okay, notice we could also write that as an ordered pair. Okay, something that I want to point out here is the following. There is a big difference between saying, hey, what is f of 5 versus what is f of x equal to 5, okay? Notice here, what we're saying is 5 is our input, what is our output? So far as an ordered pair, we have 5, and we would want to know what f of 5 is. Can we find that? Well, yeah, let's just use the function that we have here. F of 5, well, again, everywhere where I see an x in my function f, I'm going to replace it with 5. And I claim 26 comes out. Now, notice here, you're not given your x value, you're given your output or your function value, right? You're told, hey, f of x is equal to 5. What we want to do is find the value of x that takes us there. Can we do that? Yes, we absolutely can. Notice I have f of x equals x squared plus 1, but we're given that that's equal to 5. Can we solve this? Yup. First we can move our 1 over, so I get x squared is 4, and then I can take my square root, and I get positive and -2. So there's actually 2 values that will take us to 5. So these are the ideas that we're going to be playing with here, and really the important thing in this section is to get comfortable with this notation. All right, so let us play around with it. but we're going to take different functions now. Okay, let us suppose that we have g of x, and let us pretend that g of x is this function. This is called a quadratic because it's degree 2. What we want to do is two things. We want to find g of 0, and then what we want to do is solve g of x equals 0. Now, this second step is a little bit beyond where we've gotten to in this class. I am going to assume that you've learned how to factor in a previous class. If factoring is funky for you, do not worry. I'm going to have an entire video just to discuss factoring. Okay? So, let's actually go through this. If I want to compute g of 0, notice I'm replacing x with 0. So everywhere where I see an x in my function g, I'm going to plug in 0. So I get 0 squared minus 5 times 0 plus 6, which is just 6. Do you have to show this middle step? Actually not, but when I'm explaining it, I like to show every step. Now, on the other hand, here we're wanting to find the value of x that makes my function equal to 0. In other words, I take my function, I set it equal to 0, and I solve. Now, we actually have a few different ways we could do this. We could either A, use factoring, B, our quadratic formula, or C, completing the square. We will be going through each of these methods. I'm just going to factor right now. Remember, when you have 3 terms and you have a squared, and there's a 1 in front of your squared term, each of those are x's. Now, remember, we need 2 numbers that multiply up to our last number and add up to our middle number. So let's first talk about the signs. How do you multiply to a positive and add to a negative? The only way you can do that is if both of your numbers are negative, right? A negative times a negative is a positive, and a negative plus a negative is certainly a negative. And I think you'll grant me negative 3 times negative 2 is a positive 6, and negative 3 plus negative 2 is a negative 5. Now, what we're going to use is our property of 0. Notice I have the product of 2 things equal to 0. Something you may or may not remember from a previous class is if you have the product of 2 things equal to 0, either the first one is 0, the second one is 0, or both are 0. So, what we can say here is, well then, x minus 3 is equal to 0, or x minus 2 equals 0. First one gives us x equals 3, and the second one gives us x equals 2. All right, so that is one example. Let's now go to another one. My next example is this. What if we're given that P of R is R squared plus 5? What we want to find is P of X plus P of 8. Now, I know this seems silly to do, but I assure you these are all tools that we're going to be building up, which will take us somewhere. Okay? Well, what is P of X? Notice everywhere where I see an R in my function P, I'm going to put in an X. So wouldn't P of X just be X squared plus 5? Now, let's compute P of 8. What does it mean to compute P of 8? Everywhere where we see an R in our function P, we're going to plug in an 8. So we have x squared plus 5 plus 64 plus 5. So we get x squared plus 74. All right. Now let's do this example. All right, let us suppose f of x is x squared plus 2. And for part A, let's find f of 2. For part B, we're going to find f of 2 plus h. Let's start there. There's parts C and D. Okay? But let's start here. If this is the way my function is defined and we want to find f of 2, what it means is everywhere where we see an x in our function f, we're going to plug in 2. So we get 2 squared plus 2, which is 6. That was pretty chill. Okay? Now we want to find f of 2 plus h. What does this mean? It means everywhere where we see an x in our function f, we're going to plug in this whole quantity. In other words, that's 2 plus h quantity squared plus 2. Okay? This is really important, especially for those of you guys who are going on to calculus. You'll be playing with this stuff. Now, I would like to simplify this. I don't like it when things are left like that. So, why don't we do some side work to assess what is 2 plus h quantity squared? Okay? Well, 2 plus h quantity squared, that means we take 2 plus h times 2 plus h. Right? When you square something, you multiply it by itself. Hopefully you remember your FOIL technique. Remember, that tells you the order in which you multiply your terms. First, outside, inside, last. If I multiply my first terms, I get 4. Now if I multiply my outside terms, 2 times h is 2h. My inside terms, I have h times 2. Well, that's also 2h. And then my last terms, h times h is h squared. So if I simplify this, I would write that as h squared plus 4h plus 4. And that is what this is. So we have h squared plus 4h plus 4, but now we need to add that 2 on. Well, combine like terms, and we have h squared plus 4h plus 6. So we've done part A, we found f of 2. We've done part B, we have found f of 2 plus h. What if now I want us to find f of 2 plus h minus f of 2? This is part C. Well, if you were just given this exercise right off the bat, it might look daunting. Okay, it looks like there's a lot going on. But I claim what we've done is we've broken it down into parts. So we're ready to take this next step. Why? Well, again, what you'd have to do is you'd have to compute f of 2 plus h. You'd have to compute f of 2 and then take the difference. But we already have computed f of 2 plus h. We've seen that's h squared plus 4h plus 6. And I claim we've already computed f of 2. We found that to be 6. Now, why did I put parentheses? Because whenever I'm subtracting something that may have more than one term, remember you need parentheses so that you remember to distribute your negative sign throughout the parentheses. That's not an issue here, but I like to kind of keep doing that so as we don't forget. Well, all we have here really is 6 minus 6. So what we get here then is h squared plus 4h. All right, one more part. What if I asked us to find this? And again, this is something that is used in calculus, so we're not doing this for nothing. All right, again, if this was the first thing that I wrote down for us to find, it would look daunting. How would we do it? Well, the first thing we would do is find f of 2 plus h. The next thing we would do is find f of 2. Then we would have to take the difference. But we did that. Didn't we already find that that's h squared plus 4h? So really, the only new step here is we want to divide it by h. Okay? Now, I claim that this is correct so far. However, it's not really in simplified form. And as you know, we tend to like to simplify things. Okay? So, what we can do is we can say, gosh, can we factor our numerator? And in fact, we can. They have an h in common. So if I pull out an h, kind of doing the anti-distributive property, well, I had 2 h's here, I pulled out 1, I have 1 left. I have a 4h here, I pulled out my h, I have a 4 left. Now I can cancel these 2 h's, and my answer is a nice sweet little h plus 4. All right. Now let's look at this example. I have 2 more examples to do. One is going to involve a table, and then the last one is going to involve a graph. Okay, so this next example, we're given this table. So I'll list out the table and then I'll explain what everything means. Let's do this. 50, 75, 100, 125, 150, 175, and 200. And this is 4, 4, 5, 5, 6, 6, 7. Not a very thrilling function, but let me tell you what this means. S stands for the number of students in a course, and N of S tells us the number of sections of the course. In other words, if there's 50 students in the class, they're going to have 4 different sections of that class running, so as to keep, the enrollment in each particular section manageable. If there's 75 students, there's also going to be 4 sections. Notice there's going to be 5 sections if there's either 100 or 125 students. There's going to be 6 sections if there's 150 or 175 students. And then when we get up to 200 students, there's going to be 7 sections. So what we want to do is just evaluate and interpret a couple different things. Okay? So, what does N, let's evaluate and interpret N of 150 and N of 65. Okay. Well, notice the function is n of s, where s represents the number of students. So what this says is when there's 150 students, well, how many sections are there? There's 6. So we'll say that's equal to 6. There are 6 sections offered. Okay? Now, what about n of 65? Well, yes, this means that when there's 65 students enrolled, how many sections are offered? Well, notice 65 is between 50 and 75, and notice with either one of those outer bounds, there's still 4 sections. So we could say that's equal to 4. There are 4 sections. And let's spell it correctly. Okay? Now, what if here I want us to solve for s and interpret n of s equals n of 125? We want to know, first off, what s would have to be. Okay? First off, we can look, n of 125 is 5. When there's 125 students enrolled in the course, there's going to be 5 sections. Well, what other value in our table will also cause them to only offer 5 sections? Well, 100. So we could say s is 100. Okay? And last but not least, let's do one graph example. And what we want to do, pretend this is a graph f of x, is we want to label the coordinates of any points on this graph where f of c is equal to 0 and where f of 0 is equal to d. Again, what this does is it reinforces the ordered pair and the function notation. Okay? What are we saying here? Well, we want to find the values of c, that's our independent variable, where our function is equal to 0. Okay? If I wanted to write this as an ordered pair, it would look like c comma 0. Where on our coordinate axis system do we have values where our y is equal to 0 or our function value is 0? I claim right here and right here. Okay, precisely on our x-axis. You can look at those as saying, hey, where are the x-intercepts? Okay, so these are the 2 places where we could have f of c equal to 0. Notice here, if I wanted to write this as an ordered pair, it would be 0 comma d. Okay, that's precisely our y-intercept, and therefore that brings us to this point right up here. All right, have a ball playing with these examples.